Okie dokie. Hi everyone. So today we'll be going through our Methods 3-4 lecture together. So my name's Michelle and I'll be kind of taking you through this lecture a little bit. So hopefully you're all in the right lecture and we can get started. So my name's Michelle. I graduated in 2018 and my VCE subjects were mainly maths and science subjects, and then I did mainstream English as well. And I really enjoyed how all of those subjects kind of connected with each other and kind of helped each other as well, particularly the maths and science subjects. So currently I'm in my final year of medicine, and I think even though we don't do as much maths as we did earlier on in kind of first year and when we were at the university, and definitely not as much maths as when I was in VC, I think the skills of problem solving and kind of deductive reasoning are still really important here. So just a quick bit about HR Notes. We've been around since 2007 and we're just making sure students like you can thrive by offering these free types of resources. And it's HR Notes' mission to support students as much as possible. So please do check out the tons of free resources available here. We've also done completely free lectures since 2015, and we've been doing all these online lectures for a bit of a while now as well. Amazing. So these are some of the resources that HR Notes has to offer. So from things like lectures to videos to whatever multimodal type of learning that you like, there's heaps of resources and ways that you can get help, like through the forum discussion. So please do have a look and see if there's anything that tickles your fancy. In terms of other resources as well, we definitely have a lot of other resources like TutorSmart and Edu Unlimited, but these are kind of resources that you can kind of have a look more into if you just go to the HR Notes website and have an exploration if you think you need that little bit of extra help or need a couple more resources to help you along. But for now, let's get into the lecture. So I would like to extend a very special thanks to all of our university sponsors, particularly La Trobe University, because they're all trying to do it for your benefit and help you learn as much as possible. So do have a look into La Trobe and their early entry program and see if you are considering it or if anything is interesting there that interests you. Cool. Okay, so let's jump into the lecture then. So how the lecture today is going to be run is we'll be going through these 4 topics, so functions, exponentials and logs, circular functions and differentiation, and then scattered through, so we'll be going through the content and kind of the basis, the really important rules that you should learn or you should have on your bound notes, and we'll also have lots of questions kind of sprinkled throughout as well, which we can kind of explore together. And do feel free to ask a lot of questions during the time, and if you have any questions or any concerns or anything really at all, do make sure to ask lots and lots of questions, and it's better now that you ask a question than you be confused in the time of a SAC or around your exams. Okay, amazing. So let's get stuck into functions. So functions will probably be the most familiar topic to you overall, and that is because you've been doing it for so many years. So since you would have started in high school maths, you would have seen things like rules or linear relationships, and those by itself is a function. So let's just kind of chat a little bit about what's really the difference between a function and a relation. And you would have explored this quite thoroughly in Unit 1 too, but just to kind of note it down here, the difference between a function and a relation is that a function is a subtype of relation, and specifically it's a subtype where if we plug in an x value, we can only ever get one y value to come out of the function. And what we can conduct here, even though it's not really part of the study design anymore, but it's a good visual way to kind of check whether what we're doing, kind of aligns with what we're thinking of. What we can do is conduct something called the the vertical line test. So if we have like a circle like this, and then we did a vertical line test, so the vertical line just goes through here, and you can kind of see that it touches at 2 points, which is not what we want, right? So compared to something which is a parabola, something like this, if we did a vertical line test, it would only touch at 1 point. So quite happy with that. So it's a good visual way to tell whether it's touching at more than 1 point. So a relationship includes all of these, so includes circles, includes really any weird and wonderful things, and it can have more than one x value going to, it can have one x value going to more than one y value, and it can also have vice versa. So you can have something like this, you can have something like this, and all of these would be kind of defined as functions. Defined as relations. All of these would be defined as relations, all three, but only this one would be defined as a function because it only touches once. And functions are essentially just machines, so we put something in and then we take something out, and that's how it kind of works. Cool. Awesome. So let's talk about what we're trying to put into the function first. So what we're putting into the function, by convention we use x quite a lot, but you'll see in application-y types of questions or questions where they give you the variables already, you might not be using just x, you might be using t or p or s, doesn't really matter. But if they do give you a specific variable that they would like you to work with, then it's quite important that you do use that variable and make sure to use that variable throughout. Kind of in the same thought process, if you introduce a variable at any time, which for example you say a or x or whatever, and it's, especially if it's part of an application type of question, or they've told you certain things, like, I don't know, if you had a court that was being formed and they told you the length, they want to maximize the area of the court, kind of those types of questions. And you said, okay, x equals to this, y equals to this, blah, 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 perimeter equals to this. So you gave them all this information, and then you ended up with, let's say, x equals to 25 is when you kind of get the maximum area. So that's good and all, but you haven't really told them what x equals to, so it's really important to kind of restate at the end that, okay, so that means that my width would have to equal to 25, and then my length would have to equal to 50 or something. So it's just important that you use the values they give you. Okay, so what we're trying to input is called the domain, and what we do is we kind of input the domain into the function, and what gets spit out is the range. So the range is the set of y values, or whatever your dependent value is called in this function, and it kind of just outputs the range of values. So domain is the input, and then we have range, which is kind of like the output side of it. Now, let's talk about the notation that we have to write it in. So the notation for functions are quite specific, and the important thing is that if somebody asks you to find a function, you kind of have to assume that when you're trying to find a function, you are going to be trying to find this whole thing. So you're going to be writing out this whole expression here. You're going to write out this whole expression here if you're trying to find a function. If you're trying to find the rule of the function, or the rule which represents it, or they mention something like the equation or any kind of that type of wording, then all you need to write is fx equals to blah, and then you're done. But if they ever mention that they want the function, what you actually have to do is do it in function notation. So include it really in real terms, like it's not that much extra information you have to actually find out. It's really just remembering the way it's supposed to be written. So it always starts with the function itself, so whatever the name of the function is. So f, g, h, they're really commonly used ones. You can really be any letter, just like you don't have to necessarily use x. You could really use any letter in the world. So f is the most commonly used letter that you'll see for functions. G, H are also used not uncommonly. You might see P, especially when we talk about polynomials. P of x is also used quite a lot. But like I said, you can really use any letter. And then the next part, so that's the first part, so we need to make sure we write the letter, and when we kind of move on to composite functions later, or when we have inverse functions, it's important, so you just basically write everything before the brackets around the x, or the brackets around your independent term. So if it was f of g, then you would write f of g like that. So you know how you can also have this type of notation as well, so you can write that, or you can kind of write, I would go with this type of notation to kind of write at the start here, just because this is hard to break down into this, but it's up to you. And if we had an inverse where it's f inverse of x, we'll just do f inverse here, dot dot. Cool. So next what we put in is the domain, so that's the input of the function, and what happens there is, like we were talking about before, it's the values which are inputted into the function, so that's where we pop our domain. So it's a is our domain. Okay, and then what we do after that is we get something called the codomain, and the codomain in methods is always going to be R, regardless of what function, how weird, how funky, how beautiful, it doesn't really matter. It will always be R here. So in fact, we can kind of get rid of the B and just pop an R there. And what that actually means is, so when we talk about the domain and the codomain, is that the range or the output of the function will always be a subset of the codomain. So this kind of like, I feel like the idea of this was supposed to represent the domain, and this was supposed to represent the range in like, you know, kind of, that's what the original idea was, I believe. But it probably didn't work out very well, so they just popped an R there for all methods stuff. So we can just pop an R there and just disregard, like, if it's good, it's useful to know that it's called the codomain and that it has vague connections to the range. But I would say if you know to maybe always put an R there, you're pretty safe as well. Okay, cool. And then the last juicy part, which is always hardest to find, is going to be the rule itself. So the rule tells you about the machinery. So it's kind of like, how does so when we put flour into let's say, if we put flour into a cake, into a machine that makes cake, versus if we put flour into a machine that makes dough for bread or something, how is that going to be different? So the machines are going to combine them in different ways. So if we kind of imagine the machine manipulating the products or whatever's inputted into different ways, that's what's going to represent the rule part of the function. Okay, amazing. So that's kind of what we think of overall as the function notation itself. Alright, so let's chat a little bit about a question here. I'll pop this into the chat for you all to kind of consider and think about a little bit, because it's a good question to kind of get started on. So let's start by just trying to work it out together and kind of chatting about it a little bit. So what we're going to do first is we're going to just draw out the function. Let me just have a drink of water. So we're going to draw out the function first, and importantly, this is something I just recommend for essentially as soon as you see something which is non-linear and has an inequality of some sort. My first recommendation, first and foremost, is going to be you must draw it out, because you can say that you can predict what's going to go on and all that kind of stuff, but I really do recommend you just draw it out, because it's going to make your life a lot easier and you can just visually see it, especially if it's a multiple choice question, because you can just draw it on your calculator and then you have something easy to refer to. Okay, cool. So we could pop this onto our calculator to draw it, but it might even just be faster for us to draw it. So let's draw a little bit of a parabola. Sorry, my parabola is a bit wonky on the side, but that's okay. Alright, so we have 0, 0 here. Alright, so then we kind of look at what the question is asking. So it's asking us about the range of f, and importantly, they've given us a domain to kind of consider. So we know that the dom of f is going to just be negative a to b. So that's our domain of f. It's going to be negative a to b. Alright, So we also know that b is bigger than a, b is bigger than 0 and a is bigger than b. So if we tried to dot in what a and b would be, no pun intended, let's just say that's b and that's a. Cool. So then we also need to find out what negative a is, as negative a should be an exact reflection across the line x equals to 0, right? It should just be a reflection along that line or a reflection in the y-axis. So that's negative a there. So because this is a parabola and negative a squared would equal to a squared, i.e. just equals to a squared overall, we can see that these two would be the same point, right? Right, so we have those points. Now, the actual points we're going to be working on is this point here and this point here, right? These 2 points is other points that we're going to be considering here. This one is not really included in our domain. So what we're going to do is we look at this one. This is an open circle, right? And this is a case of trying to look for the absolute maximums and absolute minimums, right? So we're looking at the lowest point and the highest points in the graph. So this is going to be the highest point because on this side it doesn't go higher than that. So it's going to be a squared is going to be our highest point. And because this was a round bracket, we're going to pop a round bracket here. Okay, so then we need to check for what's our lowest point. So we can check it's either going to be at special points like turning points, or it's going to be at a endpoint, right? So we look at our endpoint, it ends up here versus our turning point, which ends up here, and we can see that actually the turning point is lower, so we're going to go with the turning point, so that's 0, right? And this is a squared bracket because it's included as part of the graph. Cool. So we can kind of see that it's going to be option E here. So it is really useful to kind of graph it out. Okay, amazing. Let's move on. Alright, so let's just talk a little bit about our maximal domains. So we talked about domains before where that's the input of the function, and we had a restricted domain before, so that domain was unrestricted, right? Because x squared really can have any values inputted into it, but we've restricted it with some sort with putting in a domain, so that we've written that right there. So what a maximal domain is for certain functions, they aren't able to take certain values just because of that's how they work and how they're mathematically defined. So when the domain is not stated, you can always assume that the domain is the maximal domain. So like for the previous question, the domain was stated, so you just have to go with that domain rather than the maximal domain. So for polynomials, the maximal domain will be R, just like we saw for our parabola just then. We can really input any values in and they would still work. However, for some functions, you can't really use the same thing of R because there are certain values where if we tried to put that in, the function would be undefined, right? And it's just mathematical type definitions and you can kind of figure it out from there. Two of the main ones that will be coming up quite a lot is going to be the 1 over x and x squared. Sorry, not x squared, square root of x. So let's think about both of them, but let's think about our 1 over x first. So our 1 over x, right? If we think of how this function kind of looks like, we know that this function kind of looks like this, right? And it has asymptotes along here. Oopsies, that's really wonky, but I don't know if it's whether should we redraw it or not. I'll redraw it, that's okay. Try to redraw it with better asymptotes. Cool, awesome. Alright. Oopsies. Oh my goodness. Drawing parabolas is always fun. Okay, finally. Alright, so that's kind of what it looks like. And we can kind of see that there are going to be asymptotes at x equals to 0 and y equals to 0, right? So what we see here is we can see the asymptotes here, and with asymptotes that evidently means that one of the numbers won't be able to be accepted. So what we're going to do here is we kind of think of it mathematically, like what wouldn't work with this function, right? So we can kind of go through all the values in our head of what wouldn't work, and we kind of figure out that 1 over 0, right? 1 over 0 to us is going to be undefined, as we would know. So it's going to be undefined, which kind of gives us a little problems, right? Because that kind of corresponds to what we think our function looks like. So that's going to be undefined. So essentially what you're going to do here is that anything in the denominator cannot be equal to 0. So when you have a function like 1 over f of x, right, you're going to actually try and solve for f of x equaling to 0 to really actually find the asymptotes and where they're located. And that works for any function you basically put at the bottom. And even when we have like when we have quotient functions where we have like h of x over g of x, what we can try and do is find what the factors of the g of x are, i.e. we can solve g of x equaling to 0 to kind of actually give us what factors can't be included. And I guess this is a bit of a fun fact which might come up in quite a tricky and exam 1 question, but if you have hx being able to be divided by g of x, so for example if you had a common factor between the two, so the factor would cancel out top and bottom, but there would be an empty circle left there because in the original function it still wouldn't be part of the function overall, right? Because it would still make the denominator 0. So we just leave an empty circle there rather than actually putting something in. Cool. Alright. Let's talk about root x. So we think to ourselves, alright, with root x, we have to think what under a root would not be defined, right? So if we kind of go through our number system again, we think, okay, broadly speaking, we think about positive numbers, right? We're like, okay, positive numbers work. What about 0? Because 0 was the problem last time. Okay, 0 should work because root of 0 is just 0. Okay, what about negative numbers? Oh, that doesn't really make any sense, right? Because no number squared is actually going to give you a negative number. That is subject to us not working in the complex plane, obviously, but we in methods work just in the real plane, and we just keep it that way, and we don't need to consider anything outside of the real plane. So what we kind of do is we say, alright, so that means that negative numbers can't be included, right? So we're going to say to ourselves that therefore the square root cannot be less than 0. So in reality what that means is if we had a root of f of x, we would have f of x is smaller than 0, right? And then we would just solve for that and exclude all of those values. And yeah, because it's smaller than 0, also that means that you'll have to graph what f of x by itself is, right? Especially if it's not a linear function. And 2, you'll actually have to solve f of x equaling to 0 as well, because you first need to find values before you can kind of decide which side of the inequality it will be on. Alright, a couple more that we want to chat about. So logs and tans, they are kind of black sheep of their own families, but they're useful ones to know, and in fact I find that those two functions are quite useful in a lot of aspects. So let's talk about our log first. So if we consider the graph of what a log looks like, it looks something like this, right? That's what our log looks like. So right away from our log, we can kind of immediately tell that we're going to be working with numbers kind of 0 to infinity, right? Well, 0 to infinity, not including 0, right? But if we didn't know what it looked like, we think of a log as a power, right? So if we had a power which was infinitesimally very small, as in very almost negative version of small, or if we had like a 1 put in here, right? Because this is essentially going to be the original, kind of like power complex, right? Because remember, if we have e of x equaling to a, then we have log EA equaling to x, and this was the original output. So if we mean that, that means that e of x, right, has to equal to something. So e of x has to be able to be equal to that something, right? Oh, sorry, e of whatever the thing is, e of, let's say, e of a has to be able to equal to x. But we can see that e of x, right, as a function, it never touches 0. So that means that x cannot be 0, right? And it never goes on the negative side. So that means x cannot be negative either. And essentially when we get a negative log, what we're implying is that something to the power of something equaled to a negative number, right? And because we're working with like all positive numbers currently, so we're assuming, we know that e is positive, it's like 2.7 something, and we're assuming that, oh, I guess you can try to not assume that x is positive. So if we try to pretend, all right, let's try and find out what's going on here. So if we did x is positive, then all is happy, we get this side of the graph. If we tried when x is negative, what that actually means is that e to the power of something, whether positive or negative, so it could be e to the power of -1 or e to the power of 1, right? That's going to equal to a negative number, which we can tell is not possible, right? Because even if you put an exponential to a really, 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 really big negative number, it's not going to turn negative. It's just going to become infinitesimally small instead. Cool. Alright, so let's talk about our tan function as well. So tan function, once again, it does have asymptotes. And why we have asymptotes, it kind of comes back to our 1 over x type theory. So tan is sine x over cos x, right? And if we kind of use our 1 over f of x, where we need to solve for f of x equaling to 0, what we're trying to solve for is cos x equaling to 0, right? And because it's going to repeat every period, we really only just need to find 1 and then add or subtract periods from it. So we know that cos x will equal to 0 at pi on 2, because kind of if we consider that unit circle, we can see it hits exactly 0 up there. Cool. Awesome. So for logs, the number inside the log must be greater than 0, and for tan, the function cannot be any n pi over 2. I guess that's also like with the pi n over 2, it's a kind of subjective thing where, not subjective, that's not the right word, kind of like, so if you had 2 pi, right? 2 pi over 2, that would equal to pi, and that gives cos a number. So in fact, instead of saying this, it should be more like 2n plus 1 pi. Oh, sorry, not 2n plus 1. 2n pi plus pi, right? Or pi 2n plus 1, right? Because it's all the odd numbers of pi is what's really actually going to get you the 0 down there. So just be careful about that. Okay. Alright, so let's move into chatting about a question now. So when we look at this question, let's have a go together. So what we want to do is we want to find the maximal domain of this question, right? We have two kind of components to consider here. The surd up the top and this denominator, right? So what we can do is actually just consider them separately and then bring them together afterwards. So what we know so far is from 1 over x, the bottom cannot equal to 0. And if we're talking about a square root, this part has to be bigger or equal to 0, right? So what that means is x minus 9 cannot be equal to 0. So x cannot be equal to 9. Cool. Alright, with this one, we're thinking, alright, so that's x minus 1 has to be greater or equal to 0, right? Greater or equal to 0. So what that actually means is x will have to be greater or equal to 1. Okay, so now we have these two types of conditions, and what we want to do is kind of conjoin those two conditions together, right? So we have x is bigger or equal to 1 and x does not equal to 9. So what we can do here is, there's kind of two ways you can kind of write it. So you can either write 1 to infinity union, excluding 9, or you can write it something like 1 to 9 union with 9 to infinity. Okay? I think this one's a little bit more difficult to write in kind of set notation or inequality notation, just because the not equaling to 9 is a bit hard to express without using these symbols in between. But it is up to you what you want to do. Right here. Let's move on. Okie dokie. Alright, so what we can see here is, now let's talk about sums of functions and how really that will affect the domain and range of them. So a sum of functions, what it really is just literally just two functions being added together. So when we consider something like x squared plus x, that is already a sum of functions because it's a parabola plus a linear graph. So we actually already know a little bit about sums of functions. Now, where it gets a bit more funky in methods is that sometimes it's not as simple as just not plain polynomial stuff. And you can have like trig and exponentials being mixed together, or trig and exponentials being mixed with polynomials, etc., etc. So what a sum of function is essentially when you've gotten two things conjoined together. It's just like best friends who are a bit inseparable. If one is not defined, the other one is not defined. Just like if one friend is not there, it's unlikely that the other friend, who is very, very close to them and will also not come to wherever the other friend is not, right? So it's kind of works in the same way. They're just like mutually bonded together about whether it's defined or not. So only if both of them are defined will you actually have an overall defined function. Rightio. So we can kind of, by doing that, we can kind of consider the graph we're looking at. So if we look at this number line, and don't underestimate the power of number lines. Number lines are actually really helpful in methods, and it kind of helps you look into like what kind of helps you picture what's going on and what you need to exclude or exclude. Alright, so we can kind of pretend to draw out the domains of a pretend f and a pretend g, because we don't really have functions here. And what we kind of get is that it only has that little section of overlap in the middle. And that little section of overlap is going to be where we get our dom of h from, because it only exists when both of them exist. So before here or after here, it's not actually going to exist anymore. So it's essentially the intersection of the two domains that really gives you the overall domain. Alright, so let's have a further look into our sums of functions. Essentially why it has to work for both functions is because we're going to input it into both functions like this. So if we had, let's say, 1 over x minus 2 and root of 4 minus x, right? What we're going to have here is when 2 gets subbed in, the first one's going to be undefined, but the bottom one is just going to be 2, right? Root 2. So what that actually means to us is that this one does not work and this one does work. So when we kind of reach this pattern here, this one is not defined, so they run from the party, but this one's still here. So because this one's run from the party, it's kind of like an electrical circuit. Now you have a missing part of the circuit because that one's run array. So now you'll no longer be able to generate an appropriate output. Okay, now let's talk about a question on this. Alright, let's talk about questions. So, we have f of x and g of x. And then we are trying to find the maximal domain of the sum of the two functions. So what we need to find out first is what are the domains of each and how do they work together. So the domain of the first one we can kind of see is negative infinity to 2. Rightio. Okay, so the next domain for g of x, we have negative 2 to infinity, not excluding both. Right? Okay, so then what we're going to get here is that we want something. We can draw a little bit of a number line to kind of consider what we're doing. And we want something from 2 backwards, or we want something from negative 2 onwards. And we can kind of see where the sweet spot is in terms of which section we want. So that section includes all 3 lines, so we're pretty happy with that, and that's going to just give us what our overall maximal domain is. So then when we do that, we can see that this one we said is 2 and this one we said is negative 2. Let's say that's 0. Okay, so remember the brackets are also really important. This one was originally a square bracket, so I'm going to just leave it as a square bracket since it's the top one. And then when we look at the other side of it, this one was a round bracket originally, and now it's the smallest part of the function, so we're going to put a round bracket around that. So essentially we'll get option D, negative 2 to 2. Alright, so let's talk a bit about composite functions now. So what a composite function actually is it's a function inside of another function. And what we can do with that is, so remember we talked about our function notation before and how I talked about an f of g of x. So another way to write this as well is just fog f. So what we have here is this, and we can also write it as fog as well. Gosh, why the pen like that? Yeah, so we can also write it as fog as well. This is really, really thin. Why can't it be thicker? That's right. That's fine. So you can also write this as fog or F-O-G. Well, that's better. Why wasn't it working before? So yeah, you can write it that way as well instead of this way. And I think that this one's actually the one published in VCE papers now. So what actually happens in a composite function, it's kind of like something going through 2 machines, like double deep frying your chicken, or deep frying and then wok tossing your chicken, or like just cooking it another way, or shredding your chicken, like cooking your chicken and then like re-majigging it when you put it into like a salad or something. Yeah, so what we're trying to do is we get something into a function, right? And then we get whatever's outputted from that function and put it into the outside function. So an important thing here, even though it might seem a little bit confusing, is what we want to do is kind of jug it along in terms of 2 types of trains. So what happens is we essentially will get it going from one function to the next function. And we can talk about it a lot more when we have the beautiful diagrams coming up in a couple of slides. Alright, so let's talk about trying to write down the rule of this, and I'll just pop this question into the chat. Okay, alright, let's have a go together. So write down the rule of f of g of x. So actually, before we can even write down the rule, when they ask you to find whatever, do whatever, the really most important thing is actually to figure out whether these composite functions even exist or not. So whether these composite functions exist or not, is really important to find out first, because sometimes they'll throw in a bit of a trick question and have it actually not exist, which is really problematic. But it's a bit of a trick, especially for like SACs as well. It's a really big trick that they tend to do, because they're trying to trick you into trying to remember that for the actual question. Oh, sorry. Just make sure the screen looks okay. Alright, looks good. Cool. So what we're going to do here is we're going to have, so we'll talk about we can just kind of briefly talk about it in terms of making sure one function can be subbed into the next function, and then we'll talk about it again in the next couple slides, but let's kind of run through it on how we would do it together. So essentially what we want to do is, in order to test whether f of g of x is possible, what we're trying to say is the outputs of g of x possible to be substituted into the inputs of f? Now, why this for this function is very unproblematic is because the domain of this is R. So as soon as you see that the domain of the outside function is R, and because we're working in methods, not spec, there's not really anything bigger than R that really can be subbed in. So we probably don't need to investigate further than that, because we already know that the domain of the outside function is R. So we don't really need to consider it further. But if it wasn't, we would have to look into what the outputs or what the range of g of x is, and then see if it fits it. Okay, cool. So in order to actually write down what the thing is, it's actually quite intuitive what you try and do. So you have f of g of x, and what you're going to do is literally just sub in the expression into there. So you're going to have of 2x plus 1 squared plus 1. So essentially your g of x is replacing all positions that you have x in. So we have 2x plus 1 all squared instead of just x all squared. Okay, so what we're going to get here is going to be 4x squared plus 4x plus 1 plus 1, right? Which is equivalent just to 4x squared plus 4x plus 2, right? So you just simplify it right down, and that's what really you're going to get. Cool. Awesome. And then you can just leave it like that, unless they ask you to do a specific type of form. Alrighty. Okay. So, like we kind of talked about before, functions are machines, and now we have the beautiful diagram that we can kind of talk about together. What we're trying to do is essentially a composite function is just two machines back to back. So when we talked about h equaling to f of g of x, what we're having is just two machines back to back. So if we kind of look at this, what this actually means is that all of the outputs of g have to go into the f. So in order for this function to be a function, once again, we have this buddy system. So if it can't, it's kind of like trying to fit a square into a circle hole. Like, you know, all those games where like you had to like fit all the shapes into like the correct holes and stuff, or like the saying that, you know, like one of those like real cute sayings about like you are the circle in like a whole like, I don't know, a whole group of like triangles or whatever. It's one of those things. So like, because essentially a square won't fit into a circular hole, what we actually need to do is manipulate into a circular shape so it fits through. Not great for talking about conforming, but you know, in the world of mathematics, unfortunately, we do have to conform to what we really need to do here. So what we have to do is change the stuff coming out of G to actually fit into what's coming to F. So i.e., what that actually means in terms is the range of G must be the subset of the domain of F. So range G, and we can use our symbol for subset, the domain of F. Alright. I like to also kind of just draw to really figure out what's going on here. We can kind of draw out, so this whole machine is going to be our H. But if we talk about our G and our F coming in here, so what happens here is we sub in the dom of G, and then the range of G comes out from there. And what we should be summing into here is the domain of F, right? We need this to conform to this. Now, if those two things aren't the same, what we're actually going to have to consider is how that changes the range of f. So if range of g is going to be smaller, as in there's less numbers, or it just like, say that was 1 to infinity and the other one was 0 to infinity, then it's going to change what the output here is. So the range of the overall function is going to be changed to something smaller. If the range of g is bigger than the dom of f, you're not going to have a defined function, and you're going to have to manipulate it until it actually fits within it. If it's equivalent, that's really the only scenario where you kind of just look at the two ends and you can get the domain of the range of the composite function. Otherwise, there needs to be some type of manipulation throughout the process. Okie dokie. Alright, so this kind of gives us an important thing of the real kind of summary of this is, in order for a composite function to exist, the range of g must be a subset of the domain of f. And that is a sentence that you can just regurgitate onto your page to kind of prove that it works or not works. Alright, so let's talk about this. So now we have similar functions to what we were dealing to before, a bit more complicated I guess, but they're asking us whether both ways it exists. A really good method for doing this is, especially if they're asking whether both ways work, is to kind of do this table method where you list out, you kind of talk about what's the domain of f, what's the domain of g, what's the range of f, what's the range of g, and how you can kind of just set it up is something like, oh, let me try and draw this so it's a bit actually nicer. Set it up so it's a bit nicer. Okay, so we can dom range g f, right? So they've kindly given us the domains already, so we're pretty happy about that. So the domain of f is r as given here, and the domain of g is 0 to infinity as given there. Okay, cool. So let's talk about the range. So in order to find out the range of basically any function, or most functions anyway, the easiest thing to do is just graph out and see what it looks like. So in terms of what this one looks like, this one is going to be looking like this. So it's going to start from -1 and then kind of go up into infinity and beyond. So what we can say about that is it's going to start at -1, right? And go all the way up to infinity. Cool. Right, in terms of g, now let's look at g. So g is going to be a square root function, so it's just going to go that way. So you can see that it's just 0 to infinity. Alright, so let's talk about f of g of x first. So in order for this to exist, the range of g, so the range of the inside, has to be a subset of dom of f. So let's talk about it. So the range of g was for us 0 to infinity, and that in fact is a subset of r. So therefore, f of g of x exists. Right, okay, let's now talk about g of f of x. So in order for this to exist, the range of f has to be a subset of the dom of g. Cool. So what that actually means is we're going to look for the range of f that's -1 to infinity, right? And the other one is 0 to infinity. And we can see that this is actually one step further than this one, so it's not a subset. There's actually a symbol for that, so let me draw the proper. So it's not going to be a subset, which we can kind of represent like this, right? So essentially it's not a subset of it. Often, so there you can say therefore g of f of x is not defined. Often a follow-up question, which is not asked here, but a really common follow-up question is kind of just asking, like, kind of make this, so how can we make g of f of x exist so it is defined? So it will be, say something like restrict f of x so that g of f of x is defined, okay? So what that actually means is now we have to say range of f now has to equal to 0 to infinity instead, right? Because it has to be restricted back. So then what we actually look at here is we go back to this and we say to ourselves, okay, what that actually means is now f of x has to just be bigger or equal to 0. So we can look here, and that's our 0 point, right? That's our line there. And the numbers here would just be 1 and -1. Because if we just made this equal to 0, it'd just be x squared equals to 1, so the x equals to plus or minus 1. So therefore, we can kind of see from here, if we need it to be bigger than 1, what that actually means is that it can be from anywhere from -infinity to -1 inclusive, because 0 is included, and then union with 1 to infinity. So essentially the only numbers you can't really take is between -1 to 1. Ooh. And then you can just put that in, and then you can also work out, so in this one, the actual overall range, so the range of g of f of x is just going to be the range of whatever g of x is, so that's 0 to infinity, so we can just pop that in. Cool. Alright. So, like we were chatting about before, if there is changes to, so if like this one, the range of f does not exactly equal to the domain of g, and then once we manipulate it, it's not exact, like for this one, it's unchanged, right? Because that is equivalent to that exactly. But if it was changed, we need to recalculate the new rule and the new domain. So what we do is we put in the domain, put in the new rule, and then kind of calculate and just graph it again. So what that actually means is that we'll also need to work out what the domain of f of g of x will become after it passes through both of them. So we kind of, once we do that, we kind of flip it backwards and see what domain changes had to do. So for this one, the new domain of g of f of x would just be -infinity to -1 union with 1 to infinity. And then the range for this one would have just been 0 to infinity. So just like this, what we can do is we essentially have domain g, domain of range of g, and then we can sub it with, what we're trying to do is we're subbing it into the domain of f, the range of f, right? Because that's what is kind of working out in terms of the function. So we just really need to be careful about what's going on here. Cool. And this next question kind of represents it quite well in terms of what we're actually trying to do. So we have these graphs of two linear functions, f and g, and we want to find the range of f of g of x. So what we're trying to do, if we kind of think back to our diagram, right? First, what we're going to do is try to sub in the domain of g, right? So we sub in the domain of g, that's -1 to 1. That outputs a range of g, which is going to be, so the domain of g was -1 to 1. The range of g is going to be 2 to 4. 2 to 4. Now, we have to check whether that works with the DOM of f. So the DOM of f is from 1 to 5. So therefore, you get the range of g is a subset of the domain of f. So that means that the function exists at least. But we note that it's actually smaller. So it's only from here to here. So that's the new thing you're going to sub into f now. So we're going to sub in 2 to 4 into whatever f to f is to get whatever that is. So we picked 0.2, pick 0.4, and for a linear function, for a non-linear function, it might be a little bit more complicated. For a linear function, you can just really pick the endpoints. For a non-linear, you just have to look whether there's any stationary points or any special points in between. But, oh, sorry about that. Go away. Alright, so what we're going to do is we can see that's going to be from 2 and that to 0. So that means that when we output that, we get 0 to 2. And that's going to be our new range. So it's going to be 0 to 2. And it does make sense, because essentially what we're actually saying here is we can see, okay, this is a rise of 1 unit. So this goes from, if we talk about like a rise over a run, so that's 4 minus 2 over 1 minus -1, right? So that's 2 over 2, which equals to 1, and our y-intercept is that. So essentially this is x plus 3. And this function here, once again, we have from 5 to 1, so 5 minus 1 over, oh sorry, that's the domain part of it. Essentially what we have here is going to be 5 minus 1 over -1 minus 3, right? -1 minus 3, yeah. So -1 minus 3 is -4, 5 minus 1, so you're going to get -1 here, and then y equals to -x, and then if we kind of try to pretend to extend this line, we would have an intercept of 4, right? Plus 4. So what we can see here is if we look at these two graphs and then pretended to kind of put them two together, what we would get here is that this would be equivalent to saying, so this is our f of x, that's our g of x. So we'll have x plus 3, -x plus 3 plus 4. So we would get -x plus 1, right? So we can kind of compare what we're trying to do here. So what we're just going to sub in at the very start is -1 to 1, and what we're going to get is 0 and 2. So if we subbed in -1, we would have gotten 2, and if we subbed in 1, we would have gotten 0. So it kind of works out in the end. Alright, let's talk about inverse functions now. So inverse functions, there's a lot to, the unit of functions is really big in methods, so there's a lot of weird and wonderful functions that we need to talk through. But inverse functions are kind of a subtype. So essentially an inverse function is just a opposite of the operation with that. So remember, functions are machines. So it's kind of like if a function was a, let's say if a function was a sewing machine, then and the inverse function of that would be a stitch breaker, right? So it's kind of like the opposite of that. Or if a function was a like doing construction, then the inverse function would be a house demolisher. So it's just trying to kind of reverse what's previously been done to it. So like this, talking about this here, doubling a function, halving a function. So those two are inverse functions of each other. Okay, so how we actually do inverse functions and actually make it into an inverse function is we take a function that takes x values and now turn them into y values, and then we can take those y values and then turn them back into the exact same x values. So what this means is that we're actually inputting y values into the inverse function, and the outputs will be the original x values. So you can kind of see that here. So the x values get inputted, and then if we inputted the same y values into the inverse function, we should get the same x values. So what that really means is that there's a relationship between the domains and ranges of the function and the domains and ranges of the inverse function. Okay. So let's chat about how we actually do this and actually write out and do the inverse function. So when we're considering something like this, where f of x equals to -4x plus 7, and they want us to find the inverse rule, so note they said rule rather than they want to find the inverse function, because if they want the inverse function, we need to include the domain in it as well. But we can kind of chat about, so in terms of the domain and ranges, they just flip, because remember what you're actually doing is you're flipping the values, so it kind of would make sense that you're flipping the sets of values that the independent and the dependent value can take, because you're kind of flipping the positions of those two values as well. Awesome. Alright, so most importantly, Okay, this is the point I want you to remember from inverse functions. If you remember something from inverse functions, just remember this point for me. You must write that you must I cannot emphasize this enough, that you must write that you need to say for inverse swap x and y. Okay, so that is the golden sentence in inverse functions. And in addition to that, you have to let y equal to f of x, okay? Because nobody knows what y is. This is f of x. Okay, so those are the two things you must write at the start. It's often given a mark in methods papers, and if you don't write it, VCA will be very unhappy with you because they'll say that you've pulled your x and swapping your x and y out of really nowhere. So that's exactly what we're going to do here. So we're going to say y equals negative 4x plus 7, and then we're going to have x equaling to negative 4y plus 7. Amazing. So now, because we want to solve our function, what we're going to do is rearrange for this. So we'll get x minus 7 equals to negative 4y, and y will equal to negative 1/4 x minus 7. Cool. So then we're not done yet because they wanted us to write the rule of this, right? And we've just written a random y thing. So then we write f inverse x is equivalent to negative 1/4 x minus 7. Cool. Amazing. Another thing I just wanted to kind of talk about briefly just before we jump into the next section is if you're doing questions, so this type of question often also does come up a little bit. So there's kind of graphical questions, especially multiple choice types of questions, which are, say, like they give you a picture and they don't tell you what function it is, but then they tell you to find which picture represents the inverse. The most important thing is literally, like, if they give you a graph, just literally draw a line on the paper, and then reflect it within the quadrants, and just reflect it across that line. So, for example, if we see something like this, we're going to think it looks like this. If it's like bump, 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 it's going to be bump, 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 right? Etc. Like, you can kind of work it out from there, but just remember that you need it to be flipped, and it's kind of just like if you're flipping across this line as well. So you just kind of consider this a mirror which they're flipping over. And I feel like that makes life a lot more easier, and it does make life, like, it does make your maths a bit, like, it's helpful, and it does make your life a little bit easier in terms of trying to do these types of questions. Cool. Alright, we'll move on to talking about exponentials and logs. So exponentials and logs, coincidentally, they are inverse functions of each other because one kind of reverses what the other one does. So essentially what we're doing is there's kind of two ways to write exponentials and logs. So exponentials by themselves, remember there's like a whole heap of exponential laws. It generally looks like a kind of exponential growth. So it looks like a function like this, and you can kind of manipulate it however you want. And its growth, and there's an asymptote. So the key features of an exponential is it has an asymptote, it has growth, it can be flipped. So it's a increasing function in its base form, and then we can kind of flip it and change it depending on what we want. So in all, that's kind of the type of thing it looks like. And remember, there is that asymptote right there. So for logs, it's the inverse function of what an exponential is. And what we actually do is, so if this was the exponential function, what we do is this is now the result, this is the base, and this is the power. So the bases are kept the same, but essentially the only thing that changes positions is the power and the kind of the result. So how I like to think of a log is logs are actually powers. So logs are powers, and like if we put that log up there, it would cancel out with that because we had log 2 to that, and then we would kind of cancel out and we just get 8 overall. So a log is a power, and an exponential is kind of the opposite of what happens. So like they're exact opposites of what they're trying to do, and that's why they work well together as well. So another way to phrase what a log is what powers do I need to raise the base to in order to get what's inside? So like I said, they are powers. Log base e's are very helpful, and they can be written as natural log, like ln, which is basically natural log because it's called the natural number. So and then you have also log ex as well, which is just the conventional form of writing it. Okay, so let's talk about how to simplify these logarithmic expressions. So there is a lot of logarithmic expressions that can be simplified and can be chatted about. So we'll kind of go through the log laws on the next slide. But maybe let's just give it a try together on how we simplify these. So the first thing that we're going to be looking at here is when we're trying to simplify a log, the easiest thing to do is look at the base and manipulate it as much as possible to get it as close to the base as possible. So we know 16 is just 2 to the power 4, so we can rewrite this as 2 to the power 4. And then the log law, which is relevant here, is that a log AB, let's not use 2 A's, a log BC is going to be equivalent to log BC to the power of A. So what we do is we kind of bring the power out to the front. So if we look here, what we can do is therefore have 4 log 2, 2, and log 2 of 2. So what power do I need to raise 2 to get to 2 is just 1. So we essentially just get 4 here, right? Alrighty, so if we do the same thing here, so log 9, 3, we'll have log 9, and we'll have 9 to the power of, so what do we need to do to 9 to get to 3? We need to take it to the power of a half. So that's going to be equivalent to a half log 9, 9, which is equivalent just to 1/2. Now this one is straightforward enough. What power do we need to raise 10 to get to 10? That's just going to be 1. And then if we look at this, log 2, negative 8. Now, we think to ourselves, okay, how does that work? Because what power do I need to raise 2 to get to negative 8? Is there any point where I can raise 2 if we consider the exponential form of it and we have 2 here? So that's going to be when it's equal just to 1, and that's going to be when it's equivalent. So that's 1, it's 2. So what point do we actually need? Like, we can see that it's never going to get to negative 8, right? Because it never gets to a negative number. So the last one is not possible for us. So it's really important that we remember that negative numbers cannot be included unless it's negative x and then you flip where the graph sits. Okay, so these are the log laws that I was talking about before. So it's really important to have this somewhere in your notes, definitely, because especially having it in your exponential section of your notes, I find it's really helpful because you can like flip to it, refer to it throughout the year as well. And just having a concise section of them really makes life easier. So if you want to take these log laws or just take it from the formula sheet or find the ones on the formula sheet and then supplement them or take it from your textbook, it's kind of up to you, but I would say definitely have a copy. Okay. So let's kind of chat through the log laws. So if we have m to the power of something, what we're going to have is just p times log am, and that kind of just relates to the third law there, log am plus log an equals to log am times n. So if we imagine m times m times m times n to the power of p, so if we imagine kind of log am times m times m, and there was p times of m in there, so like p times of m being squared, i.e. m to the power of p, then what we would have here is, if we try to separate that, it would be log am plus log am plus log am plus log am, and then onwards from there until we kind of reached p of that, so we can just times it out, and that's how that kind of law was derived in the first place. So what happens here is how this actually works is when we minus powers from each other. So when we have e to the power of 3, e to the power of 3 minus 2, or e to the power of 3x minus 2, what that actually means is just e to the power of 3x times e to the power of negative 2, right? Or otherwise known as e to the power of 3x over e to the power of 2. So that's exactly how it works here. So when we minus powers, what we do is we're dividing the products of them. If we're timesing powers, what we're doing, if we're plusing powers, what we're doing is timesing the products of them. So timesing the outputs of them. And this rule is derived from, I guess you can say it's derived from this rule or from this rule, because either way it's the same. So 1 over m would just, you can either write that as log a1 minus log am, or you can write it as log m to the power of negative 1, and it's going to give you the same thing. So if we follow along with this rule, so log am, m to the power of negative 1, pop the negative out the front, or we can follow this rule as well, so that's log a1 minus log am. Log a1 is just 0, so it's just going to equal to negative log am, and log a1 is 0. So just like e to the power of 0 is 1, log e1 is 0. And if we look at the graph, that's also what we kind of figure from there. So that's the position. Cool. Right. Another important rule that's often used quite a lot is the change of base rule. So the change of base rule is essentially, like the name suggests, a rule that's useful for changing base. I haven't seen it used that much like in isolation, because normally log questions, especially in exam 2, they're like in combination with differentiation and stuff. But I can say that it will definitely be helpful in terms of differentiation and integration, just because you actually can't differentiate a non-natural log. So you can't differentiate 2 to the power of x just by itself. You actually need to convert its base to e of x before you can do it. So kind of keep that in mind a little bit. Cool. So there's kind of two. This is the main change of base law. So how I like to think of it is the a goes at the bottom, the x goes at the top, and then you just put whatever base you want here. So it's kind of like ax, so ax over a, right? And then if we just wanted to flip which one was over which, right, all we have to do is just kind of just change it to 1 over that. All right. Okay. So let's chat about this question a little bit then. I feel like this question's a good question considering it's a big question in the first place, which is always very exciting. So let's kind of talk about how this works. So the expression log xy plus log yz, where x, y, and z are all real numbers greater than 1, is equal to, and then we need to kind of consider what we're choosing from there. So the first thing that we kind of can notice from this question is that there is a changing of bases throughout this question for most of these, right? So we have yz here, yz here, yz here. Okay, so the only two which don't have the change of the base is these x and y, x and y. So first what we can do is kind of rule out or rule in those ones first to kind of consider whether those ones are correct or not. So log xy plus log yz, is that equivalent to 1 over log xy plus 1 over log yz? And if we have a bit of a think, we realize no, it's not equivalent, because if we can kind of get tricked. So this is kind of just bringing up the thing of log y 1 over z is not equivalent to log y z all over, so 1 all over that. So just keep that in mind when you're, just be careful about that. But essentially it's not equivalent because we're flipping the two, but we don't really know what's equivalent to on the other side. And even if it was equivalent, the plus would need to be at the bottom down here. So no, it's not equivalent. And in the same manner, this one wouldn't be equivalent either, because we're just adding negatives out the front. It's the exact same thing here. Okay. Now we need to consider the changing of bases, right? Because we've changed our bases for all of these. So what we're going to do here is now try and change the base. So we're going to pop the y at the top, and we're going to try and change it so we need y and x to be together. So we might as well just change the bases all to y here. So we have log y over log y x, and we could have used the second rule here, but if we didn't remember it, we can use this one, plus log, then this one has z here, and we need z there, so we can do z over log z y, right? So log z over log zy. So that's just going to give us 1 over log yx plus 1 over log zy. Cool. So we kind of already know that this one is the correct option, but we can always check. So once again, this is just negating the whole process. So even though this is true, this may not be true, right? Because even if this is true, that's timesing everything by -1. And if we times everything by -1, it might not necessarily be true anymore because we've times by -1, so therefore we've changed the result slightly. And this one, once again, just like how we couldn't flip this one into this one, we also can't flip this into this. So kind of rule those out. Okay, amazing. All right. So in terms of graphing a logarithm, the base form is just essentially like this. So you have an asymptote at x equals 0, and then you have 1 equaling to here. This is the transformed one. So you can have any base, but the most important thing is that you recognize where the asymptote is, and you recognize on which side of the asymptote it is. So there can be a negative there, or can be a negative there, right? And if we kind of consider what happens, if we have this being negative, right? So we have a reflection in the x-axis. What happens instead is, so if we originally had this, we'll now have a graph that looks like that instead. So that's what's going to happen eventually, and that's what it's kind of going to look like there. Alright, so then what if we tried to reflect it here? So what if we had a negative in front of here? Now, instead of looking like this, our graph is now going to look like this, because now all the negative inputs are going to be the inputs which are used, and only the negative inputs can be used, right? Because if we have a negative and a negative, that makes a positive, so that's the only inputs that can be used there. So this is if we had a negative x, and this is if we had a negative a. The d doesn't really make that much of a difference overall, really, but I guess if you have a d, you no longer have that like, it just kind of means that you have to find where the x-intercept is a bit more. It just makes finding the x-intercept like a little bit more complicated. Cool. So let's talk about these 2 points. So why does this asymptote exist in the first place? So why this asymptote exists is essentially when we go from the number 1 and closer to 0. So let's just talk about this graph here of just 1 of a log 2x, right? Let's just talk about that one there. So if we just kind of consider the one of log 2x, what we're actually going to do here is we're going to say that that's going to be like the asymptote is at x equals 0 because there's no horizontal translation. And essentially when we get closer and closer, so when we come from 1 and get closer and closer to 0, right? So let's say we have log 2 a half and log 2 1/4, right? So if we compare those two, this is going to be -1 versus this is going to be -2. Let's kind of put that to extreme, and now let's go log 2 1 over 1204, which is actually -10, right? So what we're doing is we can see as we're getting more fractional, we are actually getting more and more negative. And eventually, we will reach a fraction which is so small that we will approach this asymptote, right? but there is never going to be a level where this stops. So therefore we have an asymptote rather than it crossing a point. Because if we tried for log 2, 0, right? What that would mean is 2 to the power of something is going to be 0. And we can say that's going to be negative infinity, right? Because 2 to the power of negative infinity will mean 2 to the power of infinity, which means that this will eventually reach such a big number that the top part doesn't matter. So that's why the asymptote exists. And we can also relate it to the E of x, because we had a horizontal asymptote here, and that's why we have a vertical asymptote there. Okie dokie. Right. Circular functions. Let's talk a little bit about them. So circular functions are also one of those things that people find really annoying, and fair enough, they are quite complicated, especially when you're graphing or solving for them. So when we think about circular functions, what we think about is the unit circle. So that beautiful circle which is 1, -1, 1, -1. In a unit circle, the easiest way to think about it is the y-coordinate is the sine and the x-coordinate is the cos. And then the tan is the gradient, so y over x. In methods, we just use radians for angles, okay? Like in 1, 2, you would have used degrees sometimes, but for 3, 4, generally everything is in radians. So if your calculator is still in degrees, I would recommend for you to pop it into radians, and then just be careful about whenever you see questions about angles or anything, just be careful about what they're actually asking and whether they're asking for radians or whether they're asking for degrees in the first place. So the next thing you need to know is how to remember your exact values. There's 3 different ways. This is the table way. Okay, so table way. So if we look at this, this is what it's going to be. So this is an angle of 0. This is going to be an angle of pi on 6. This is going to be an angle of pi on 4. It's going to be an angle of pi on 3. And this is going to be an angle of pi on 2. So just remember, those are the key angles you need to remember. There's 3 different ways. 1, the hand method. 2, table. 3, triangle. This is my preferred method because it's the least memorizey. People do use the hand method as well. Look up a video on YouTube. It's quite beautiful. You basically just like count over the fingers and then count backwards to kind of figure out what's going on. So it's also quite good, but you just need to remember the order of the angles quite specifically. Table is good, especially if you're regurgitating a lot of numbers that you need to use. But I find, so the 2 triangles that for this are the first triangle, which is the 1, 1, root 2 triangle. So that's the pi on 4 triangle. And the other triangle is the 2, 1, root 3 triangle, which is the pi on 3, and this one is pi on 6. And using the triangle, you basically use SOHCAHTOA to find out what each of them are. Cool. Alright, so solving. There is 2 kind of different ways to talk about solving. So the easiest way is to rearrange for a simple equation. So what you're going to try and do is put everything outside of your sine, cos, tan to the other side. So you're going to chuck everything onto the other side. Then what you're going to do is try and find the base angle. So what angle would correspond to the value on the other side? Now, for sine and cos, you want 2 solutions. And why you want 2 solutions is if we consider sine, right? The 2 solutions are located, they're located here and here. And for cos, it's located here and here, right? Because sine, if we think of the one, it's ASTC. So you can do cast for the ones which are positive. Alternatively, you can look at which side's positive, which side's negative, x-axis, y-axis as well. So if we consider sine is positive in those 2, cos is positive in those 2. And we can kind of see like the actual like solutions, they're not evenly spaced from each other. So that means for cos and sine, we need to find 2 solutions per cycle, versus tan, because the positive solutions are here and here, so they're evenly spaced from each other. So that means that we actually don't need to that's why our period for tan is only pi rather than 2 pi, because it actually is evenly spaced compared to these 2. So we need to find 2 solutions for sine and cos. Alright, so then you do a quadrant check, which quadrant it is, and you can find two solutions for between 0 to 2 pi, and then you just add or plus or minus 2 pi until to fill out the domain, and then you can solve for x. Alternatively, you can kind of skip this step and just solve for x first, and then what you do is you add whatever their period is. So add period. So if their period was 2 pi and 3, you add 2 pi and 3. If their period was pi and 4, you add pi and 4. If their period was 2 pi, you add 2 pi. So let's have a go at doing that. So this needs to be solved over an interval of 0 to 4 pi. Alright, so the first step, we're going to move everything around the sign to the other side. So that's going to be sine x will just equal to a half. Now a second step is to find the base angle, which means we need to refer back to what we were kind of looking at before, so the triangle. Right. And we identified that we want the 1, 2, root 3 triangle here, so 2, 1, root 3. So that's going to be our pi on 3, and that's going to be our pi on 6. And remember, this triangle is just derived from an equilateral triangle with 2, 2, 2 on each side. Okay, so what we can see here, that's 1 over 2, and we want sine, right? So 1 over 2 would mean it needs to be the opposite of whatever it is. So 1 over 2, that means that it needs to be pi on 6. So our base angle is pi on 6. Alright, let's do our circle next. So in terms of our unit circle, we're going to think it's here and here, right? Because we're thinking these are the areas which their y coordinate is positive, so that's where sine is positive. So the two angles we're going to be thinking of is pi on 6 and pi minus pi on 6, right? So that's x equivalent to that. And we'll have x equivalent to pi on 6 and 5 pi on 6. Okay, cool. Now we need to check for the domain. So those two solutions are in domain, happiness. So if we checked minusing, that would become negative 11 on pi and negative 7 on, negative 11 over 6 pi, and that would become negative 7 over 6 pi. So that's outside the domain, so we don't want to go backwards. Now we can check with forwards. So if we go, that's pi on 6, that's 5 pi on 6. Now if we go forwards, that's plusing 12 pi on 6. So we're going to have 13 pi on 6, and the other one is going to be 17 pi on 6. And we can check those, so that would be 24 pi on 6. And that's going to be within domain. Alright, if we tried to add 2 more pi, immediately we can tell that if we added that would be 25 pi on 6. So it's already outside domain. So these are our final solutions. Okay, so those are kind of you might get a question or two of those in exam 1 or one of your stacks. Importantly, you also might get questions like this where you kind of have compound functions which you need to solve together. And people get really freaked out about these, and kind of fairly so. So what we want to actually do is you want to think back to your polynomial knowledge. Pretend that all of those causes are just a's and you're just factorizing as much as possible, okay? So what you want to do is group like terms, factorize as much as possible, and then treat the causes like x's, and then solve for cos afterwards. And then it's going to apply the same way when you have an exponential as well. Sometimes you'll have something like e to the 2x plus, I don't know, 5e to the x minus 3 or something, and you'll freak out and the first time you see it, and then you won't freak out after that, because all you need to do is just sub in a equals e to the x, and then it just turns into a quadratic which you can solve, and then you can kind of revert backwards after. And it's the same for kind of these circular functions. So whenever you see something a bit unfamiliar and it's in exam 1 and you know, oh, I can't use my calculator for this, there's going to be some method where you kind of replace one of the factors to make it more comfortable and to make it something you know better. Cool. Yeah, and never divide out factors, just in general, not just in circular functions, just in general. You will lose solutions. You can always remove solutions after and say, oh, this is why I'm removing it, but you can't just like kick them into space, outer space, and not tell why we're kicking them out into outer space. Okay, so general solutions are a way also to represent circular functions, and there is formulas for general solutions which can be given in like your books and stuff, so you can have a look at those. I personally don't find them like they're good, right? But I didn't use them that much in VCE. I kind of just build it up a different way. and I always found that worked out better because it just made a little bit more sense to me. But you can see which one works better for you, whether you prefer the formula more or you prefer this method more. It's kind of up to you what you want to use. And because of the cyclic nature of the unit circle, we can really get infinite solutions. And that's why we go for general solution. So if they don't give you a domain, they're asking you to find the general solution. Okay, cool. So it's asking us to find the general solution of cos x equals to tan x. Alrighty, so 2 cos x minus tan x. And why I'm taking it to the other side first is I want to avoid any instance of me just randomly removing solutions. That equals to 1. Alright, so the first thing I'm going to do is I'm going to rewrite this tan x as sine x over cos x. Right? And that's going to equal to 1. Now, what I'm going to do after this is I'm going to change this so this is all over the same, like just basically times everything by it. So I'm going to get 2 cos squared x minus sine x equals 2 cos x. Right? Cool. Then once again, what I'm going to do is just move everything to the other side. So 2 cos squared x minus sine x minus cos x. And that now equals to 0. Cool. So then what we can do after this is we can kind of consider like what we want to in terms of the grouping and how we can group the different things together, right? Because now we have our cos x's and we have our sine x's, all of these kind of all together now. So what we can do here is we have our 2 cos x squared. So just like for this previous question here, when we had our 2 sine squared x times cos x minus our cos x, right? What we can do here is we can kind of do something similar where we're going to try and take out the components that we already have, right? And we're going to try and take out like what we can see which is common between the two. So if we kind of move back onto this page, the first thing that we can kind of take out here is going to be our cos x, right? Which is kind of going to revert us back to here. Wait, let me just rub that out. Okay, so what we're going to try and do here is, so we need our 2 cos x equal to be equivalent to our tan x. So let me think of a good way. Oh wait, yes. So a good way to do this is not to write 1 on the other side. Okay, oopsies, sorry guys. This should just be 0. Because I cannot minus. Apologies for that. Alright, so let me just write in a 0 here. Because when we took tan to the other side, it should equal to 0, shouldn't it? Alright, so when we put that onto the other side, now we can times everything by that. That would still equal to 0. Okay, so now what we can do is, so we've got this cos squared x now is equivalent to kind of this negative sine x, right? So if we kind of consider, this as cos x minus our tan x, and we have a look at our kind of unit circle, right? Oopsie. Why won't this work? Oopsie. Okay, I'll just use it on this side. Right away, for what we can actually tell from this one, using our knowledge from talking about minimal domains and stuff like that, is that cos x will not equal to 0, right? So we know that x immediately cannot equal to pi on 2 or 3 pi on 2, or basically, if we talk about in general solutions, it can't equal to 2 pi plus 1 over 2. Yeah. So then we kind of go back to this cos squared x minus our sine squared x equaling to 0, right? And we want to change this so it's something that we can deal with now, right? Because we have this cos squared x and we have this sine squared x, and we kind of figured this out already. So what we're going to do here is we're going to just plug in 1 minus sine squared x minus sine x equaling to 0. Because remember, cos squared x plus sine squared x equals to 1, and that's our Pythag theorem, which is really helpful, right? So if we removed kind of to get cos squared x by itself, kind of change that to the other side. So now what we're going to get here is 2 minus 2 sine squared x minus sine x equaling to 0. And we basically, like I talked about before, we now have this squared part, which is really hard to deal with. So we're going to just change that to a, and instead now we're going to have 2 minus 2a squared minus a, and that equals to 0. Now we can kind of just do a bit of a quadratic type of thing. And what we're going to do here is we're going to say a is now equivalent to 1 plus or minus root 4ac, so b squared minus 4ac, so that's negative 1 squared minus 4, a, which is negative 2, c, which is just 2, over 2a, which is negative 4, right? So we get that. Alright, so then we get a equals to 1 plus or minus, and we can note that that's going to be negative 2 times 2, which is 4, so negative 4 times 4 is going to be negative 16, right? So that's going to just be 16, negative 16. And then what we're going to get here is that it's just going to be equivalent to, so 1 plus that is going to be 1 plus or minus 17 over negative 4, right? Okay, so you can also rewrite this as a squared plus a minus 2 as well if we wanted to. Doesn't really matter either way, I guess. Alright, so then we get to this part, which makes life a little bit trickier, I think, because now we have this fraction. I definitely don't think this is something you probably can solve by hand. So then we can go to our trusty calculators to try and find what it's equivalent to. Algebra solve. And I know it kind of can seem a bit silly to revert to our calculators now, but sometimes we do need to get it into a specific form. And I think that this form was just not something that we could unfortunately do by hand. So let's plug this into our calculators. Just make sure it's on radians. Hopefully my calculator doesn't do the wheel of death, but it did give me a very approximate answer, which is definitely not a good sign. So it gave me that, let's try and just solve this so we can actually find what our thing is first. 2a squared plus a minus 2 equals to 0 for a. So yeah, so essentially it's giving us numbers which are like x equivalent to 0.895 ... and that's in radians, by the way, so however many of that, and then x equals to 2.24 ... So essentially after this step, if this equaled to like a half or something that was easy to do, you would just make it equivalent to sine x, and then you can solve from there. But unfortunately, because it is equivalent, so those are our two base angles, we can convert these to degrees, because it might be easier to work with. Well, it doesn't really matter either way. So the main thing is that we can see here that the period of this is just going to be 2 pi over 1. So it's just going to be 2 pi. So it's going to be whatever this is, plus 2 pi n, plus 2 pi n, because we're just adding the period, so it should be the same. Then we're going to say where n belongs to z. Cool. Awesome. So yeah, that's kind of how it works. if this was a nicer number, we probably could do it fully by hand, but because it was a bit of a gross number, we couldn't really do it by hand for the full process. But once you get to this step, if this, in a question which you can do by hand, you should get a half or something, or like a half, root 3 on 2, 1, root 2 on 2. That's really the only things you can really get. Cool. Alright, so in terms of graphing, the easiest thing, let's just talk through the graphing, kind of the steps. So the steps I like to talk about is do period amplitude, do a dotted line at the mean line, talk about where the mean and the max are. Then you determine the quarter or the step size, and you divide the period by 4. And what you do is you kind of dot those periods along. And then what you can do after that is find out where it starts. So when it is at its max or when it's at its min, and then just kind of dot those along from there, and then you just mark the important points from there, and then you just repeat until you get more periods. Cool. So let's put this into practice a little bit. So I'm going to start off with my amplitude, and my amplitude is 2 here. My period is 2 pi over 1, so that's just 2 pi. My max is going to be 2. My min is going to be -2. And my mean is just going to be 0. So that means that I don't need to find x-intercepts for that one. Hurrah. Okay. So then after this, I find what my step size is. And my step size is going to help me determine how often I move from my max, my mean, to my min. Okay. And that's how often I'll move. And that's going to be 2 pi over 4, or otherwise known as pi on 2. Then I'm going to choose where it starts. So x minus pi on 2, if we consider like the kind of just the normal graph of what a cos graph really looks like. A cos graph kind of looks something like this, where it kind of goes like weep, weep, and kind of goes like that, right? So this will be at pi, and this will be at 0, and this is kind of at pi on 2. Now, we have this minus pi on 2, which means that it's actually shifted right pi on 2. So what's going to happen is now my top point is going to be here, and now my bottom point is going to be here, and this is going to be here, right? So now my maximum is going to be at pi on 2 instead. So what my starting point is going to be pi on 2, and I can see that's pi on 2, 2, right? So starting point. Right. And then you're basically ready to do. You could also find x-intercepts, but for this one, it's not strictly necessary. So let's make sure we label our axis appropriately. And if you're able to kind of label it appropriately, I really recommend you kind of choose your own spacing, because it does make your life a lot easier. 3 pi on 2, pi on 2. Cool. And I'm going to say 2 and -2. Okay, so I know I'm going to start here. And then what I'm going to do is move my step size, so that's pi on 2. And when I do that, I'm going to move to the mean line, either side. Right? Okay, so I've hit the edges of my domain on the 0, so I don't need to go back further. Now I just need to go forward. So I've hit pi, right? Now I'm going to move forward another pi on 2, and now I'm going to go from my mean to my min. Okay, cool. Now what I'm going to do is now move another pi on 2, and now I'm going to go back again to my mean. Alright, now then we just join the dots. And we are done. So that's pi on 2, 2, and 3 pi on 2, -2. Then we have 0, 0, pi 0, 2 pi 0. Okay, so generally in a circular function graph, what you have to label are the min, the max points, and the x-intercepts. If your mean points don't hit the x-intercept line, I'll just not label it, because you already label so much stuff, it just makes everything a bit messy, so I would just not label those. But for this one, because it hit the x-intercepts, we have to label them. Okay, amazing. Alright, let's talk about differentiation. So these are your common kind of differentiation functions. So you have polynomials, we have exponentials, we have circular functions, and we have logs. So all the stuff we've talked about so far. Importantly, lots of the formulas are in your bad notes, so that really saves you in exam 1 and kind of gives you a reminder of what to do. So these are all the formulas that you can kind of actually use. I think the important thing to kind of point out is you can do this without Like this one's really helpful. This is kind of like a chain rule but already done for you, so that's really helpful to know. And this one also is a bit tricky because it actually turns into a kind of like not a polynomial, but I guess it turns into a polynomial like thing, right? And these ones, the important thing to remember is this turns into sec, which is 1 over or a over cos or whatever, 1 over cos squared. And this is negative while this is positive. Alright, so there's a couple of rules that we'll just chat about before we actually try to differentiate a function. So the first one is the product rule. Like the name suggests, it's used for products, so when a function is times by another function. How I like to describe it is I diff one, leave the other, diff the other, leave the one. Okay, and that's how I remember it in my brain. So what I do is essentially, if you want to set it out really nicely, what you can actually do is you can name these u and v and use the like Leibniz type notation. So you have u equals to x squared, v equals to x plus 3, and that way you can say du dx equals to 2x, and then dv dx equals to 1. And then you can kind of just put it, so if I diff one, leave the other, so x squared, and then diff the other, leave the 1, and then put times those together. And then you kind of just make sure everything's simplified, so you get 2x squared plus 6x plus x squared, which is just going to equal to 3x squared plus 6x, and then you just leave it. So diff the other, leave the 1, diff the 1, leave the other, or diff 1, leave the other, diff the other, leave the 1. Essentially, you can also set it up like this and just do like a crisscross match as well. Cool. Alright, chain rule, it's used for our composite function, so our f of g of x. So it won't be written as a composite function, it will just say what it is, so g of x equals to blah. But you'll note that two different functions are combined together. So what you need to do is just diff the inside, keep the outside. So diff the inside, diff the inside, diff the outside, keep the inside. So what you do is you leave the inside, pretend that it's inert, and you diff the outside, but then you can't just really do that because that means you're not really considering this a function. So you just diff whatever's on the inside as well. So you just need to care for both parts. So you care part 1, part 2. And I guess for this one, once again, you can also do like a u and v type situation as well if you want. Okay, so let's go through this one together. So we have cos e to the 2x, and hopefully you're saying that this one will be equivalent to your chain rule because you can kind of see that it's a composite function. So importantly, we kind of need to consider that. So if we look at this, we see that it's y equals to cos e to negative 2x. So we know that this is the inside and this is the outside, right? And I guess another way you can write, so if we have f of g of x, another way to write the derivative of that is f dash g of x and then g dash of x. So what we can do here is e to the power of negative 2x, that's just going to be negative 2 e to the power of negative 2x, and either x I really like because you just basically put whatever's in front of the x out the front. So that's diffing the inside. Now we diff the outside, keeping the inside the same. So cos diffs to negative sine, and that we just keep e to the negative 2x on the inside. Alright, so if we kind of simplify and just connect all of those together, we'll just get 2 sine e to the power of negative 2x e to the power of negative 2, e to the power, so 2 sine e to the power of negative 2x. That's all we need. Oopsies, sorry. Negative 2 e to the power of 2x sine e to the power of negative 2x. So it should be negative here. Cool. So yeah, just write it all together and just kind of simplify and clean it up a little. Okie dokie. Alright. So like I said, logs are a bit trickier, and this rule is super duper useful. So just make sure to kind of make use of that and have that in your formula sheet or bound notes in some form or some matter of form essentially. So you want to have this in your bound notes because this is useful for differentiation, yes, but it's super duper useful for integration especially because sometimes you'll have something like they'll be like integrate tan of x dx, right? And there's no like formula for integrating tan. So what you actually have to do is split it up into sine x over cos x, right? So this is anti-differentiation. And then once you do that, you can kind of see that it's basically in this form and you can just manipulate it from there. So when we have f of x, essentially we just need to go f dash of x over f of x. That also makes our differentiation easier as well, because the chain rule, remember, it's diff the inside and then keep the outside with the inside being the same. So it would just be f dash of x. And then because log ex is just 1 over f of x, it just works out to be simplified into this form. Alrighty. So let's give that a try now. So if fx equals to fx equals to log ex cubed, find f dash x. So what that's going to equal to here is, we know that this inside is our hx or our fx from before. So what we're going to do is diff the inside, which is 2x squared, and we're going to put that over the outside, which is just x cubed, which essentially we can kind of see that cancels that, so it's just 2 over x. So that makes it really nice, simple, clean. Alright, let's talk a bit about stationary points. So those are the rules itself and how we actually derive and do all of that stuff. So let's talk about how we actually can use our differentiation. So when we derive something, what we're trying to find is the gradient of the function, right? So when we find the derivative, a synonymous for that is we're trying to find the gradient. So that kind of enables us to find stationary points, and the word stationary points kind of gives away what type of points there are. They're literally when they have zero gradient, so it's not moving, so that's when there's a zero gradient. So what we're going to do therefore is try and find when f dash of x or dy dx equals to 0, and we can solve for the x coordinate using that. There's 3 points at which we can kind of get a stationary point, and these are turning points, so local mins and local maxes, and stationary points of inflection. So those are the 3 points that we can actually get a stationary point at. No other point on the graph will really be a stationary point. So once we solve for stationary points, so once we solve f dash of x equaling to 0 or dy dx equaling to 0, we can then determine their nature. So there's kind of 2 ways to do this. We can either sketch the graph, which can be easy for some and can be more difficult for others, right? Because like for a cubic or something, we kind of know the general shape of it, so it's okay to graph. But for something which is a bit more funky, it's probably a bit gross to do. And in fact, you are probably finding the turning points and stuff to actually help you know what the shape of the graph looks like. So you can use something called like a gradient table if that doesn't work. Which is finding the gradient immediately before and after. We'll do both methods kind of here to talk about how it works and how we can use it together. So it wants us to find the stationary points of 2x cubed minus 3x squared minus 36x. And so the first thing is we want to find what f dash x is. So even if you don't really know what's really going on, but you get the vibe that you'll have to do something with differentiation, just derive. You'll get at least 1 mark, because you've at least done the first step. So if we try and find what f dash of x here is, or more appropriately dy dx here, because everything's in terms of just y, it will just be 6x squared, so we took down the power, reduced the power by 1, minus 6x, so take down the power, reduced the power by 1, and then minus 36. Now, we're now going to try and find the stationary point, so that means that dy dx equals to 0. So we'll have 0 equals to 6x squared minus 6x minus 36. So what we're going to do is now we can just divide everything by 6, so we don't need as big numbers. So it'll just be x squared minus x minus 6. Cool. Now we can kind of factorize them into 2 brackets. So that's going to be x minus 3, x plus 2, right? So therefore we'll have x equals to 3 or x equals to negative 2. Alright, so now we need to determine the nature of these things. So we can kind of just have a go at determining the nature. So there's, like I said, there's 2 ways. There's really actually 3 ways. There's also something called the double derivative as well, which I guess the use of it's not encouraged in methods, and I wouldn't really use it in your SACs, but it should be fine to use it in your VCA exams. So just keep that in mind as a method as well. And it's essentially when you just find the second derivative and then you sub it in. We can just have a brief chat about that as well. But essentially what we can do here is we'll just kind of set it up. So we can just graph it actually instead. So we'll know that this graph approximately, I'll probably need to find the turning points and everything then. Okay, that's right. Let's try and find the points, like all of the turning points and stuff. So not the turning points, the x-intercepts. So if we subbed in 2 there, we would have gotten 16 minus 12. So that's negative 28. So that's not quite right. No, that's too big. Okay. What about 1? So that's 2 minus, no, that's definitely too big. What about negative 2? So that's going to give us negative 8 minus, no, that's too small. So then 3. So what I'm just doing is just the factor theorem for the polynomials. 3, so that's going to be 27. Negative 54. Negative 54 minus 27. Oh no, negative 54 minus 27, so negative 61, negative 81, and then that times by 3 would be 18, 108. Okay. If we had, if we were allowed to graph this on our calculator, just so we can make sure to get through all of the content, 2x cubed minus 3x squared minus 36x. Okay, so I guess one of the points would just be 0, right? It's a good point to take out. So it's points pass through 0, and then we have 2x squared minus 3x minus 36. And then we can do like quadratic formula on that. But we kind of know that the general shape is going to look like this, right? Because it's a positive cubic, so it's going to look something like this. And therefore we can tell that this is going to be the max and this is going to be the min immediately. So we're pretty happy like that. That's one of the ways you can do it. Another way you can do it is via the gradient table. So what you do is you just put in the points, and so I'll have negative 2 here and I'll have 3 here. And I like to sandwich this, so I have to find one less point. Just makes life easier. So this is x, this is f of x, and this is what the lines look like. So at negative 2, we should get 0, right? Because if we get negative 2, that's going to just equal to 24, you know, and it should give us like the number that we need, right? Because we should get, so negative 24 plus 12 and then minus 36, so we'll get 0 here, 0 here. We can do 0 in the middle here, and then do negative 3, and then I would just do 4 here. Just 2 like simple numbers is better. So if we sub in 0 here, we'll get negative 36, which is smaller than 0, so it's going to go down. So we'll have 0, so these are flat lines. And then we'll have negative 3, so negative 3, so that's going to be 9 times 6, so that's 54, plus 18, so that's going to be 54, 64, and then 72, so 72, then minus 36, that's going to be positive 36, now that's going to be up. And then we're going to sub it in 4, so 4 squared is going to be 16, 16 times 3 is 48, so that's 96, so 96, then minus 24 is going to be 72. Once again, it's going to be 36 here, so it's going to go up as well, and we can kind of see down, down, down. So once again we get the local max and then local min as well. Cool. And then in terms of the second derivative, so f dash dash of x is going to just be equivalent to 12x minus 6. So if we sub in those 2 points, so negative 2, f dash dash of negative 2, that's going to give us negative 24, negative 30. So if that's smaller than 0, it's a local max. If it's bigger than 0, it's a local min. And if it's equivalent to 0, we don't really know, but it's a point of inflection of some sort. Cool. All right. Optimization problems are essentially like an application-y type of question. And essentially what they just want you to do is just maximize or minimize the quantity of something. So there's a lot of applications which involve this. The main thing is that we really need to be careful about finding the absolute maximums and absolute mins rather than local maxes and local mins. So what you essentially want to look for is 1, the local maxes and local mins, and then 2, the endpoints. So 1, local max, local mins, 2, endpoints. And that's really only the points you need to check. Okay, cool. So another application that you can have here is finding the angles between something. So it's just remember the relationship that because we're finding the gradient, and gradient is rise over run, i.e. tan. So if we just equate the gradient, so when we find the gradient by subbing in values into the function, we'll get m, and then we can just equate that to tan, and then from that, what we'll actually get is just the gradient of the function, which will kind of make our life easier, right? So we can just find it from there. Alright, so this one, find the angle from the positive direction of the x-axis to the tangent. Remember, it is always the angle from the positive direction of the x-axis. So whenever you find an angle, whenever you do a tangent, always from the positive direction x-axis. That's because the unit circle, remember, goes that way. Alright, so at -1, and you can see measured in anti-clockwise direction because of the unit circle. So f dash of -1 is going to be equivalent to -1 over root 1 minus 2 times -1, right? So that's going to be -1 over root 1 plus 3. Sorry, 1 plus 2. Got ahead of myself. So that's -1 over root 3. Now, we're going to equate that to tan theta. And if we draw our little triangle here, we have root 3, we have 1, and we have 2. If we want 1 over root 3, that's going to equal to our pi and 6 because we want kind of our opposite over our adjacent, and it's going to be negative as well, which means that it has to be in this quadrant, right? Because we're talking about angles up to 180, and this is, I guess, a special circumstance where you use degrees. I feel like this is used more commonly here. So it's going to be in this quadrant, and it's going to be pi and 6, or otherwise known as 30 degrees. Therefore, this angle should be 120 degrees, right? So we're going to say theta is therefore going to be 120 degrees. Cool. All right. So then what we can kind of do here is we want to consider what else we want to do. Oh, sorry, not 120 degrees. What am I talking about? That's pi on. This is 30 degrees, so 150 degrees. Sorry, because it's pi on 3, meaning pi on 6, not pi on 3. So it's 150 degrees. So then what we can kind of consider here is so it will be essentially just be if we pretend that was a function, right? At that point, the gradient of the tangent would be going like this. So we'd have an angle kind of coming from there. Alright, in terms of angles between lines, you can use this compound angle formula used in Spec. Alternatively, you can also just look at the picture as well, but this formula is helpful. So it's m1 minus m2 plus m1, m1, m2. Cool. So if we try and find the acute angle between these two lines, so we'll have 1/3, which kind of passes through here, right? And then we'll have 2x -1. So, no, sorry, that should be going up. So it should be going, so we'll have 1/3, so it'll kind of be 1/3, 3, and it'll kind of vaguely look like this, and then we'll have 2x and -1. We'll have something looking more like this. That's probably not very to scale, but so they're essentially asking us to find the angle here, right? And we know we can find the angle here and the angle here. So if we look at this, we can either find these angles separately and then kind of use that, or we can use the formula from before. So if we use the formula from before, so tan theta would equal to so it was equivalent to m1 minus m2. So it kind of doesn't, I would say it it doesn't really matter which one you consider M1 and M2 because eventually you are going to end up with the same angle. But I guess you can kind of tell. So if you end up with an obtuse angle here, you kind of just do have to use logic to which angle you really pick. So I would say we have to try and keep it positive, especially if we're trying to find, so it tells you it finds the acute angle. So like you can kind of use your logic here. I'm going to go with 2 minus 1/3 just because I think that's going to give me my positive result. So then it's 1 minus my M1 times my M2. So that's going to just be, 1 plus my M1 plus my M2. So what I'm going to get here is that it's just going to be that it's 2 times 1/3. So that's going to equal to 2/3 over 5/3, right? So alternatively, that's going to equal to 2 over 5. So my theta is just going to equal to tan inverse 2 over 5, right? So this formula can be really useful in that manner. Cool. Okay, and that kind of wraps it all up. So kind of just to summarize, make sure to functions, make sure you consider whether you want function rotation of the rules. Be careful of maximal domains. In terms of logs, be exacting and be careful with graphing near asymptotes. Don't flick up or away. In terms of circular functions, be systematic in finding solutions and graphing, and always just follow the clear steps, and you can find shortcuts once you're more comfortable with that. Differentiation, just try and identify the correct rule and then do any vibe that you need to differentiate, just differentiate because you might get a mark from it. And so just keep on trying different application questions, keep on having a go, and do exam style questions early on to kind of really adapt those exam environment questions and try and time yourself as well to be efficient. Cool. Alrighty, we shall wrap up there. Thanks everybody for listening. I will see you all around, and good luck with any aspirations you have, and good luck with methods.